In this video, we want to look at a couple examples requiring substitution that are slightly more complicated than the ones in the previous video. But again, we're confronted with a situation where a piece of the integrand looks a lot like the derivative of another piece, right? 10x to the fourth looks a lot like the derivative of our power here. So let's go ahead and begin by letting u be that power. Then the differentials, du, will be 5x to the fourth dx. Now our differential here does not show up exactly in this integrand, right? But 10 is just 2 times 5, right? So I can rewrite this integral as 5x to the fourth e to the power dx. And the 2 times 5, I'm going to move the 2 outside the integral, just so everything inside the integral matches up with my substitution exactly. And again, constant multiples, you can move them inside or outside the integrand. So if we just move the 2 inside and multiply by the 5, we'll get back to our 10. Okay. So at this stage, all I've done is rewrite the integrand so that the substitution matches up exactly. So now the integral in terms of u will be 2 times the integral. 5x to the fourth dx is du. And this is going to be just e to the u, right? We chose u to be the power on e. So the antiderivatives of this, 2 times e to the u plus c. So all that remains is to distribute the 2 and replace u with our x to the fifth minus 2. So that'd be 2e x to the fifth minus 2 plus c. Since c simply stands for some constant, 2 times c is also just some constant, so we can simply write it as c. Let's look at one more. This is also a problem very similar to the last video. In the last video we had a 9 in the numerator, and the 9 was exactly the derivative of the denominator, so we let u be that denominator. We'll take the same substitution here, and we get that the differential du is 9 dx, right? But we do not have 9 dx staring at us in the integrand, but I'd like to see it just so my substitutions match up exactly with what I'm looking at. So, 9. To have a 9 in the numerator, right, we must have multiplied this by 9. So to balance it out, in other words, to make sure we haven't changed anything, I'm also going to have to multiply by 1/9. Just because 1/9 times 9 gets us back to where we started. So now rewrite the integral in terms of u. 9 dx is exactly du. And our denominator, we chose our u to be the denominator, so we're left with 1/9 times the integral 1 over u du. That's 1/9 natural log of the absolute value of u plus c. Distribute and put x's back in. We get 1/9 natural log of the absolute value 9x minus 10 plus